So, in the first lecture, I told you about how Einstein reached this special theory of relativity. The driving things were the electrodynamics experiments and the so called unsuccessful attempts to find velocity of earth through ether. So, two postulates I wrote last time. One is principle of relativity, I will talk on that in more detail, and the second was that speed of light is same in all inertial frames. Speed of light in vacuum, it's same in all inertial frames independent of whether source is moving or not moving or who is observing which inertial frame, it is constant. So, these two are the postulates of special theory of relativity. Now, this constancy of speed independent of frame, that comes from a famous experiment which is known as Michelson-Morley experiment. So, Michelson was the senior person and who measured speed of light also using his own design of experiment and did many other things, and Morley joined him to further improve the sensitivity accuracy of the experiment, and this very famous experiment is perhaps the one Einstein is referring to, that unsuccessful attempt and all that. So, let me go little bit into the history of this, or history of light itself. So, as you all know, Newton has done a lot of work on light. He had done lots of experiments using sunlight through a window, small hole in a dark room, and prisms and everything. On colors he has done a lot of work, experimental work. So, all these things are listed in his book Optics, right, Optics by Isaac Newton. A detailed description of all those experiments and the results are given here, and he has tried to explain all those results by taking light to be particles on which forces act, and then the particles accelerate, particles move in straight lines with constant velocity if forces do not act, and all those things like that. Then you also know that contemporary was Christian Huygens, who looked on these experiments in a very different way, and he proposed that light should be a wave. And these things went on. There was no exclusive experiment which can decide that it is wave or it is particle till say the beginning of 19th century, when Thomas Young came up with a double slit experiment and showed the interference of light. So, the interference is some kind of a signature of wave nature, and there, and together with many other experiments, speed of light in water is less than speed of light in vacuum, and many other experiments by Fraunhofer, Fresnel on diffraction. So, those things combined, 19th century beginning 1801 to 1805, let us say, it was established that light is a wave. But then wave needs a medium. That was the understanding. What is wave? Sound wave, for example. So, essentially sound is nothing other than the vibrations of air molecules in a particular fashion. So, when sound propagates, we say that okay, this part of air is compressed or rarefied, and then it exerts force on the other neighboring part, and there you have compression and rarefaction, and that is how the wave propagates. So, the understanding was that there must be some kind of a medium in which this light wave propagates. Then comes Maxwell and experiments on electricity and magnetism, and two things. One is that once you do the experiments, find epsilon naught, find mu naught from the experiments, and then put the values, and you see that this 1 by square root epsilon naught mu naught turns out to be very close to 3 into 10 to the power 8 meter per second from purely experiments on electricity and magnetism. You do an electricity magnetism experiment, get the value of epsilon naught, get the value of mu naught, and then calculate this, and it turns out to be this, which is very close to speed of light. And this establishes that there is some close relation between this light and this electricity and this magnetism. And then comes Maxwell, who writes the entire theory of electric field, magnetic field, charges, currents, and all those. And those Maxwell's equations I am not writing the equations, that will be in the course on electrodynamics, but these equations tell that one can have electromagnetic wave electric field and magnetic field propagating like a wave, and that wave will have a speed which is once again this much. So all this connected tells that okay, light is an electromagnetic wave and its speed should be this much. But if the speed is this much, with respect to which frame? So when I say speed of sound is 332 meter per second, with respect to what? With respect to air in which this sound is propagating. Is the air which is carrying that sound wave, and the velocity, the speed of sound is 332 meter per second at 0 degree Celsius in a frame in which that air is stationary. In this room, if air is stationary and I am speaking, yes, the sound is going at that particular speed. Of course, here temperature is not 0 degree Celsius, so it will not be 332, it could be 345 meter per second or so. But with respect to what? With respect to this stationary air. But if you have wind, then in the direction of wind, speed will be more than this, and opposite to the direction of wind, the speed of sound will be less. In the frame of that air, the speed is given. So if the speed is given, the numerical values is given, it must be with respect to something. And what something? Very naturally, the medium which carries this light, the vibrations of medium portions, they are taking this light wave ahead, and it is that medium which should be taken as the frame with respect to which this speed is measured. So that is how that idea of ether came in, that there should be a medium, and people named that medium as ether. And then the search was on to locate that ether, and it was assumed that that will be absolute rest, because that is the frame, in which light has this speed. So that should be the frame in which all Maxwell's equations should be correct. And if I go to some other frame, Maxwell equations should not be correct strictly. So these were the dilemmas, these were the questions, people were wondering on these, and in that scenario, Michelson came up with an excellent, fantastic idea how to measure the speed of Earth in that so-called ether in which Earth is moving, and that is this Michelson-Morley experiment. But before that, let me show you an interference pattern to give you some idea what is that interference, how does it look like, and how it is related to when I will say this Michelson-Morley experiment and fringes and this and that. So you will connect it better if I show you some kind of an interference pattern here. So essentially interference means at the same place you have two waves coming in, and these two waves which are coming in and superposing at that place, they have some kind of a phase difference, and because of that phase difference, when they superpose, you can have a very large intensity or a very small intensity. So when the waves combine to give you a large intensity, you say it is constructive interference, and when the waves combine to give you a low intensity, you call it a destructive interference. So I will just show you an apparatus in which an interference fringe will be formed. You will see the fringe. What do I mean by fringe and bright fringe and dark fringe and all those things. So let me show you the apparatus. So it is a very simple apparatus. Here is a laser torch. We are giving some power to it, and the laser is already on. You can see it here on my hand. You have spot, and the beam is going like this. So the beam is going this way, and then it is falling on a plane mirror. You can see the mirror, and you can see a green spot somewhere here. You can see a green spot somewhere there. So this laser beam is falling on that mirror, and from there it is reflecting, and then it is reflecting back and going to a wall. So this beam after reflection is going to a wall, and there you see a spot. So very simple thing. If you have a mirror, if you have a light beam, the beam will be reflected from that mirror and will fall somewhere. But there is something beautiful about it. Once I dim the light of this room, you will see that it is not just a spot, there is a lot of structure in it. So let us dim the light and refocus on that spot on the wall. You can see the variation of intensity of light. You have circles, green circles and then dark circles alternately. These are called fringes. So how come you are getting all these dark and bright circles? We had shown you it is a simple reflection from a mirror, and the spot falls on a particular point on the wall. But when I dim the light, you see it is not just one spot, it is a pattern of bright and dark fringes. So the light is reflected from the front surface of this mirror glass and also from the back surface of the mirror glass, and these two waves together fall on the wall. So at different points of the wall, if you see, the phase which comes from the front surface and the phase which comes from the back surface, they are different. They are taking different times, and therefore at some places you have constructive interference, at some places you have destructive interference, and you see all these patterns. And if I shift this mirror little bit, rotate this mirror little bit, you just see where it is dark, a bright may come there. This whole pattern can shift. That is what I want to show you. So now I am working on the mirror. Look at this fringe pattern now, and now I am just slightly rotating, and you see what is happening. Can you see the fringe shift? Fringes are shifting, right? The positions are changing. The position of the bright, which is now any bright, you focus on any bright ring, and then see what happens as I rotate this mirror little bit.